discussing the proof of the splitting theorem in the context of RCD spaces. I guess before entering into that, there is one last thing I want to say about RCDK infinity and RCDK n spaces, about the structure of geodesics. Basically, I want to prove the Riemannian theorem in this setting. This will turn to be useful in a couple of situations. And for what concerns the splitting theorem, I recommend, so I wrote a sub, so the original paper is long, it's like 100 pages, and it is based on another previous paper of another 100 pages, but I wrote an overview on the proof of the splitting theorem, which is 50 pages in total, and that's, I recommend that as at least as a first reading. There are a couple of details missing, but instead the details missing are hopefully, it should be clear that there are just technical, they are not crucial ideas that are sort of omitted in this overview. All right. So a first theorem that I want to prove today. Now, before going to the splitting, a word about optimal maps. And here is the first result. And this is a theorem that comes by a combination of efforts of myself, Rayal, and Sturm, in a 2.5 papers. And the theorem is the following. So say that X is RCD. And say that you have, let me put this way, you have two measures. Let me be a bit lazy, in the domain of the entropy. Well, then I could actually let me say absolutely continuous. Hi. Then there exists a unique optimal plan. Actually, I could say, let me put this way. Then there exists a unique W2 geodesic from nu to nu, and a unique lifting of it. Okay, so in particular, there exists a unique optimal plan, and is used by map. It comes from a map. Let me see if what I wrote makes sense. There exists, and sorry, and is induced by a map. Now, and it is. Okay, what is it I'm saying? Let me repeat what I'm saying. So pick an RCD space, pick two measures, both absolutely continuous. Okay, both. So that marks a clear difference with respect to this statement of Brunier or Mecan theorem. We are imposing something also in the target measure. Okay, then what happens? There exists a unique Barthes-Stein geodesic connecting these two. First of all, this Barthes-Stein geodesic, as any absolutely continuous curve, emits a lifting, but this lifting is in fact unique. Okay, and moreover, it is also induced by a map. This means that there exists a map T that goes from X to geodesics on X, such that our lifting pi is T push forward mu. Mu is our starting measure. Okay, for almost every point there exists a unique R. Okay. Now, in particular, there is only one optimal plan between mu and nu, and it comes from a map. But anyway, actually, let me just stick to the uniqueness of the lifting. So what it is saying is, look, I want to go from my absolutely continuous measure mu to my absolutely continuous measure nu, and how do I do that? Well, there is only one geodesic and only one lifting. Okay, makes sense. So this is so if you are on a Riemannian manifold and you forget about the absolute continuity of the target measure, this is basically Mecan's theorem. Okay. Now, interestingly, the proof of this result has nothing to do with the ideas of the proof of Mekan's theorem, of Brownian theorem. It is actually more related to ideas by Champion and de Pascale. They used the idea that I'm going to discuss in a second in the setting of RD and for cost equal distance for generic for a distance coming from a generic norm, and to prove existence of optimal maps. And in fact, it has nothing to do also with counterlogic potentials. No? Nothing to do with dual problem and whatever. So it's much more geometric proof. And the idea is the following: take so these are okay. Of course, these are probability measures with finite second moment. I forgot to mention. Otherwise, there is no geodesy. Sorry. So there is a geodesy connecting them, let's say, and pick a lifting. Okay. Now, suppose this lifting does not come from a map. Then there exists. Okay. So suppose the lifting of the geodesic is not induced by map. Well, then, by definition, there exists, the set, what can I say? Let me put it this way. So there exists a set E inside X Borel with positive measure, such that for almost every X in E, there are, if I look, so I disintegrate pi with respect to the projection onto the first marginal, no? And I look at this set, and I look at what it is, I should say, the diameter. I want to understand when it is that pi x. So basically, in order for pi to be induced by a map, pi x, the disintegration should be a delta for almost every x. So if it is not induced by map, pi x is not a delta for almost every x, and therefore the diameter of this guy is bigger than 0. That's so basically by definition of not being induced by a map. All right. Okay, but then there exists E and there exists R, such that also this set has positive measure. There is a positive mass above a certain threshold of values. All right, now with that, so so now there is a technical point, but let me say, so in particular now let me say up to a measurable selection argument. In fact, it's a Borel selection. So Borel selection, I could find two maps, say T1 and T2. These are both maps defined say just on this set E with values on the space of geodesics, with the following properties. So Ti of X always lives in the support of pi of X, for almost every X. Not Lebesgue, sorry, M almost every X. And second, the distance in the space of geodesics between T1x and T2x is bigger than, I don't know, say R over 2 for M almost every X. I mean, of course, M almost every X, in E. Make sense? Just in sense. Pick T1 just satisfying this, And then there will, given that this condition is satisfied, you have room to find also T2. I'm not saying anything, okay?
The pi x here, when you write the limit of pi x bigger than r, it's like the support of your integration. The limit of the support.
Of course. Sorry, thanks. Absolutely. Yes, of course. I had this in mind. And maybe also I said, but sure, the diameter of the support. Thanks. Yeah, I have this idea. So for almost every x, I have a measure uniquely defined. I look at the support. So this bigger than r for almost every x is a the statement that makes sense. Okay. Okay, I should verify that the amount that takes x and returns the diameter of the support is Borel. So that okay. All right. Now, let me see if let me actually look. Let me be a bit lazy because I have to fix a mistake in here. So I mentioned that there exists a geodesy between mu and nu, right? And actually, to be honest, this is cheating, right? Because I know on RCD or CD space, I only know that geodesics if I start from measures in the domain of the entropy, a priori. Okay. Let me actually rephrase this with a much stronger. So let me say that these two measures have bounded density. Anyway, then in the finite dimensional case, we can simplify that. And here is for the following. I do this for the following reason. Let me think 1 second. Well, perhaps look. Let me do this for you. So let me describe what's the idea, and then I transfer technically this. So the idea is this: suppose you are in a situation like this, where you have a compact space, a compact set, and on this compact set you have defined two maps, and these two maps actually, yeah, maybe I'm already at that. So, and I have T1, T2, T1, T2, and what you know is that if you take this compact space and you follow just the path of the first map, then the entropy is, sorry, not the compact space. You pick the measure restricted to this compact set and normalized, and then you move it according to the first map, say T1. What you obtain is something with entropy which is convex, and the same with T2. Then, well, this is not possible basically, unless the measure of this compact set is 0. Okay, and why is that the case? Well, because if say that let sigma be the measure restricted to this compact set normalized. This is case. Okay, and say that now say sigma, I don't know, 1t, is just et push forward t1 push forward sigma, right? And suppose that the amount that takes t and returns the entropy of sigma t is k convex. All right. Well, then if this is the case, now let's wonder how big is the support of sigma t, or actually how small can it be. The support really meaning the measure of theoretic sense. So write sigma t. Well, if it is convex, then sigma t certainly must be absolutely sigma 1t. Sorry, must be absolutely continuous. Let's call the density rho 1t m. So, and now I question how big is the set, where rho 1t is strictly positive. And the question, of course, rho is an m almost everywhere defined function. So this set is defined up to negligible sets, but its measures is well defined. Okay. And my claim is that the limit, that this cannot be too small, because this limit must be at least the measure of where actually the measure of k. Okay. And why is that the case? It's basically by Jensen's inequality and convexity. Because if the entropy is convex, what we know, in particular, is that the lim sup of the entropy of sigma 1t is less or equal than the entropy of sigma, no? Because by convexity it stays below. Okay, and if it stays below, okay, I should pay a little bit of attention here, because it could be convex, but it could be that, you know, at time 1 it is plus infinity, so it could be in principle in trouble. Let me exclude this. So this lim sup of the entropy should be, you know, less or equal than the entropy of sigma, but the entropy of sigma, we know how much it is, right? We've computed already several times the entropy of the reference measure restricted to a certain set, and that is minus log of the measure of k. Okay, but on the other hand, by Jensen's inequality, what it is that we know. So the entropy, who is the entropy? Who is the entropy of the measure sigma 1t? Well, that is the integral of rho 1t log of rho 1t, right? The m. But of course, this integral I can certainly restrict to the set where rho is positive, right? This rho. Well, then let me normalize the integral. So let me put this way, and let me multiply a measure of this set where rho is positive, what it is, to the -1. No, without -1. Okay? Multiply and divide by the mass of this set. Okay. Now I'm in position of applying Jensen's inequality. Let me rewrite this. This is measure of this set where rho is positive times the average integral of u of rho is rho 1t dm, right, over this set where rho is positive. Make sense? Right? But this is greater or equal, right? By Jensen's, u is convex. So this is greater or equal than I have this mass, and then I have u of the average integral over the set of rho dm. Right? But this we know how much it is, right? That's because rho integrates to 1, and we are averaging. So this is you know, all this is what this is 1 over the mass of this set, right? So this is again, it's 1 over the mass log of 1 over the mass, and so this is minus the mass of this set. Right? You plug this here and you get this inequality. Right? Mm-hmm. I said, but I didn't write. Sorry. Minus because it's one from the log, right? Make sense? Okay. Okay, what's wrong? This should, but sorry, because it's cancelled. Yes, so thank you. Log of them, only log of the mass, only log of the mass. You plug it there, minus simplifies and log. Thanks. Yes, thanks. I was sloppy. All right. Well, what's wrong with that? Well, with that, what is wrong is that now we have a situation where following the red path spreads out. I mean, this model tells that the mass is a little bit spread out. Following the blue path, no, what is this? How can this be blue outside and green inside? Following the green path, look, it's blue. And yeah, following also this other path is also, you know, spreads out the mass. But also, in some sense, as a part of the assumption, also following both together is still optimal. Okay, so here we have a situation where now let's follow both paths together, and okay, again here is the contradiction. K is compact, right? So you can find a little open set containing it, so such that the mass of this open set is smaller than, say, 3/2 of the mass of K, if K is positive measure. If K is positive measure, you can find an open set U containing K, such that this is true, right? Now, for T very small, all these sigma 1t and sigma 2t will have support in the in this open set U. And for possibly taking t smaller, they have they should be concentrated on a set which are of comparable size as k. In particular, for t very small, we should have that the set where where rho 1t is positive and the set where rho 2t is positive, this should have intersection. No? The mass of this should be totally positive. But this contradicts the essential non-branching. What is happening in here? What this is telling? This is telling that there is some point here that comes both from a red path from some guy and from a green path from some other guy. And this happens on a set of positive measures because of mass constraint. Right? But this is not possible. Okay, by essential non-branching. And RCD are essential non-branching because we know that. Okay. Right. So in fact, okay, now from here is a technical, it's verifying that I can actually make Borel selections, that when I go along these measures, the entropy remains finite, it does not blow up, so everything makes sense, etc., etc., etc. And this is a matter of playing a little bit with this assumption, but nothing conceptually too hard. Right? All right. So this argument is the argument of my paper on optimal maps. Then Riemannian came when I assume non-branching, actual non-branching, and then Riemannian proved that RCD spaces are actually essentially non-branching, and this was enough to make the argument conclude. Okay. All right. Now, so you see no Kantorovich potential, no nothing. It's just a non-branching business together with this observation, I would say. Okay. There are also, by the way, there are workshops. Let me mention also that this sort of argument extends to the setting of MCP MCP spaces by as it has been observed by Cavalletti and Mondi. Now, what is I want to say? Let me, I want to now to improve from RCDK infinity to RCDK n with finite n. And what I gain by putting n is that I will have to impose nothing on the target measure. Okay. In some sense, as far as you continue to live and work in RCDK infinity, you have to put something also on the target because otherwise you have tightness problems. You have basically you have nothing because RCD or CDK infinity really speaks about measures with finite entropy. But as soon as you put a finite n at the technical, there are technical simplifications, and perhaps in fact let me state in the form of a proposition something that we have learned from the last lecture. So let sorry, perhaps maybe I should have clarified. So what it is, so this argument that I was proving, I mean, just to show that maybe, so this argument that I was proving, what does it say? It says that I cannot, so who is K? No, K would be a compact subset of E here, right? And then once I have this compact subset, I can forget about my initial and target measure. I just replace my initial measure with the uniform distribution on K, right? So, and this argument proves that any lifting of any geodesic must be in fact be induced by a map, right? And this proves the uniqueness of the lifting, and also then the uniqueness of the geodesic, right? Because otherwise, if you have two different liftings, you take pi1 plus pi2 over 2. That's a new lifting which is not induced by a map if the two were different. Okay. All right. So now let X be RCDKN. And when I write n, I implicitly want to mean that n is finite. Okay. Let's mu t equal rho t m. Let's say t to mu t be a W2 geodesic. well, then, and pi be, let me say, elliptic. For the moment, let me say elliptic. Well, then, what we know is that rho t gamma t to the power 1 minus 1 over n, this is greater or equal than sigma 1 minus t k n distance gamma 0 gamma 1 rho 0 gamma 0 to the minus 1 over n plus the symmetric, sigma t, etc. And this holds, then for every t, this holds for pi almost every gamma. Okay. Where does this come from? This comes from the local, from we had the integrated. So the CDKN, or actually CD star KN, is means writing this in the integrated form. Okay. But then after the essential non-branching, we can start from a lifting and restrict to a set of, if this fails for a set of geodesics of positive measure, I restrict my, lifting to that set. That would be, another plan where, I should have the inequality, but I don't, and so that's contradiction. Okay. If you want, I could perhaps, notice that given that I assumed this measure to be absolutely continuous, if this fails, I can assume that it fails on a set of geodesics where both rho 0 and rho 1 are bounded, so I can apply, the statement above where once these are bounded, there is only one, geodesic, connected. All right. Okay, so in particular now let me just work with the case k equals 0, which is the relevant one for the splitting, just for simplification. Anyway, I mean all the formulas, are more complicated, but they are valid. Even in more general case, if k equals 0, this reads as rho t gamma t is, I think, well, let me guess it. So this should be rho t gamma t. This should be less or equal than 1 over 1 minus t to the power n rho 0 gamma 0, if I correctly remember. In particular, plus, okay, I could write plus 1 over t to the n rho 1 gamma 1. Do I really want this? No, I don't. No, I don't. Let me see. Make sense what I'm saying? Oh, where is it? Oh yes, actually yes. So what I get, so let me write all the steps. So if k is equal to 0, then sigma 1 minus t 0 n d is really 1 minus t. The k, the n, and the d disappear. Okay, so then you see I get rho t to some power greater or equal than 1 minus t rho 0 to some power plus some other term that if I want I can throw out because it's not negative. Okay, and then you raise to the power minus n and you get exactly. All right. What else? Okay, yes, and now comes the theorem. Yeah, I know. Corollary. Corollary of this statement. And notice that, so perhaps let me emphasize this. The possibility of writing this, so a bound on rho t, on this just in terms of rho 0, is really something which is finite dimensional. On RCDK infinity, you cannot have this. Okay, and this is related to the fact that basically, there is, the entropy blows up if the target measure becomes more singular. Okay, so you're gonna get this. Okay, and the corollary of this is that, look, say that you have, x RCDKn. Actually, let me say RCD 0n. But there's an analog statement with k, and mu nu probability measures with, say, mu less or equal than some constant times n, but I assume nothing on u. Okay, then there exists a geodesic, geodesic connecting them with mu t less or equal than 1 over 1 minus t to the power n actually cost. For every t, in, say, 0, 1 excluded. I mean, in 1, that's nothing. Okay? Proof. If mu also was absolutely continuous, then pick the geodesic connecting them, and notice that for this geodesic, this bound holds. And therefore, for this geodesic, this bound holds. Pass to the limit. Given that you approximate your target measure nu with absolutely continuous ones, even with bounded density if you want. When you let it go to 0 or epsilon go to 0, this estimate remains there. That does not depend on epsilon. This kind of estimate is stable by weak convergence. If you have a sequence of measures mu epsilon t satisfying this bound and this converge weakly somewhere, you must. Okay. And what about how can you be sure that there is enough compactness? Well, recall that CDKN spaces are doubling, so they are locally compact. And so once you're in locally compact space, if you have a sequence nu epsilon that is converging W to some limit nu, you start building geodesics. This geodesic must converge. You have enough compactness to conclude. Make sense? All right. And now here is the theorem, which again is by the same authors. And it is if you want, the finite dimensional improvement of this. And you can think both as a theorem about optimal maps or as a theorem about the possibility of making exponentiation in metric measure space, in RCD spaces. So let's say that X is RCD. Okay, I write 0, but okay, you can read read K if you want. This works even for K. And let's say that you have two measures, mu nu, probability measures. Actually, let me put it differently. Say that you have phi from X to R, which is a Kantorovich potential, a C concave. C is distance squared over 2 as usual, and locally Lipschitz. Okay. Then for almost every X, there exists a unique guy, P of X, in the C subdifferential of phi of X. Okay. And in particular, if I have two given measures, actually, if I have, well, let me put it this way: if you have two measures, let me say, well, let me put it this way. So if you have one measure, which is absolutely continuous with respect to n, mu is in P2, then there exists let me say at most one W2 geodesic mu t with starting from, with mu0 equal mu, and for which phi is a Kantorovich potential. Also, this geodesic has a unit lifting, and this geodesic, and this geodesic, and let me put it this way, and t push forward mu is the only lifting. Okay. Let me read this statement. Once we prove that for a certain, say, class of for one potential you have this statement, then it is clear that then Riemannian theorem applies. How do we prove Riemannian? We prove that we have a convex function. Convex functions are differentiable almost everywhere. Therefore, by the link between differential and C subdifferential, for almost every point there exists a unit guy over here, and then we are done because by generic Ottoman transport business. So once you have this, the rest follows the same sort of line of thought of the proof of Riemannian. Okay. All right, let's prove this. By the way, so one comment: why here I'm speaking about existence and uniqueness, while at the level of measures I only pointed out the uniqueness and not the existence. Well, just because if it exists, so it's there's a problem of the total cost should be finite. So I did not quantify the local ellipsis regularity in here. So in principle, if there is a geodesic, so basically the distance between mu and the target measure would be integral of distance squared x t1x d mu x. But this in principle could be plus infinity. So in some sense, it could be that following this geodesic brings us out of P2, and therefore we don't have finite distance. But as soon as this is finite, that the geodesic also exists. Okay. So how do we prove this? Well, so first of all, so existence is a consequence of the local ellipsis regularity. And local compactness of the space. So proof. Why do we have existence? So what does it mean? So I'm looking, so fix, so actually existence there is for every x. So say pick x, pick a point, and pick, so I'm looking for an element in the C subdifferential. So I'm looking for minimum of what? Of the mark that takes y and returns distance squared x y over 2 minus phi of y. Right? So well, pick a minimizing sequence that for sure exists. So pick yn minimizing sequence. And notice that if this yn remains on a bounded set, then bounded sets are relatively compact, so I can pick subsequence converging somewhere, and then it's clear that any limit is actually this desired minimum. Okay, so I only have to exclude that dxyn goes to plus infinity, right? So let me say that this is the case, and let me pick gamma n geodesics, let me say constant speed geodesics, parameterized, geodesic from x to yn. All right, and let me call Zn the point along the geodesic, at value 1. Let me say. Now, Zn is for sure a bounded sequence, right? Because actually the distance between Zn and x is identically 1. Okay. And now let me notice the following. What should I notice? Yes, I should notice that. So how much it is? Phi of Zn minus phi of x. Let's see. So I want to say that this, actually, I want to say that the lim sup of this is, let me think 1 second. I want to say this is less or equal than the lim sup in n of minus distance squared Zn, Zn yn. So why is this true? Let me think. Is this correct? What is happening with yn? So yn is tending. So let me think. So this is written in my notes, but it's not justified, so I have to think. So what it is that is true? So phi c at x. So this is equal to the lim in n of distance squared x y n divided by 2 minus phi of yn. But of course, phi. No, I don't like this. No, but phi is c concave. Sorry, phi is c concave. So given that phi is c concave, I know that phi c of so wait a moment, phi. I would like to put there phi of x. Let me think. Minus phi c of y. Yes, this is so. This should be true. Is it true? Look, I have to draw the picture. If I draw the picture, I understand this. So what does it mean that phi is c concave? Phi c concave means that phi is the inf of parabolas. The graph of phi is the inf of parabolas. Okay. So the fact that yn is a minimizing sequence for this guy means for phi of x means that phi of x is the inf over over n of distance squared x y n divided by 2 minus phi c of yn. So the yns are vertex of parabolas basically. So okay, but on the other hand, phi of zn is also for every n. This is also less or equal than the distance squared zn yn over 2 minus phi c of yn. Right? And now, so this is true for every n. If you want, this is, so we can put it this way, plus epsilon n if you want. With epsilon n, it goes to 0. Okay. And now we have done, because now what I can say, look, let me take out the lim sup. So what I know now is that this minus this is less or equal than this, say, minus epsilon n. Actually, epsilon here morally, okay, if I want epsilon positive, I should put the minus here. So this makes a little bit more sense. Okay. Now, here Zn, now here the point is that Zn, actually, let me draw the picture. Let me show you with the picture what is happening. If the vertex of the parabola goes very far from x, the steepness of the parabola at x increases. Make sense? But if the steepness increases and goes to plus infinity, how can phi be locally Lipschitz? Okay. In practice, what is happening over here is that we actually know how much it is this distance, because the distance between Zn and Yn is the distance between x and yn minus 1. Right? So if I I can plug this, take the squares, the distance square simplifies. I get here something like minus distance between x and yn, okay, plus constant. Right? For every n. But now you see that if you let n go to plus infinity, this blows down to minus infinity, but phi was real value, it was local ellipsis. How can this be a ellipsis function if at distance 1 from x I found a point whose value is as little as I want? Okay, so this proves existence. All right. And what about uniqueness? Now the almost sure uniqueness is comes out of this, and more or less morally the same argument that I was giving before. So suppose, actually, let me just draw the picture. So suppose that uniqueness fails. So uniqueness fails means that there is some compact set and two maps up to Borel selection, whatever, such that both these maps, I have the T1. Okay, so I have the maps are T and S, and I have the T of x evaluated at time 1 belongs to the C-sub differential of phi, and the same Sx evaluated at time 1 belongs to the C-sub differential of phi at x. Okay. Suppose you have this case. Now what do? I want to exclude that this happens for a set of positive measure. So let's pick a compact set K where these two guys are different. And now what do? I start with this measure, as before, and then put pick a T1 pushover sigma. This is a measure that can be singular. I don't know. I have no idea. It doesn't really matter. I have some measure, and what I know is that phi acts as a counterweight potential for this mass. And I can certainly also, up to restrict K, I can also be sure that both T and S are bounded maps. So that this integral is finite. I don't go to plus infinity. It's just for uniqueness, I can pick this set as small as I want. But now what I know is that there exists a geodesic connecting them for which that bound holds. Right? So in particular, I have absolutely continuous evolution. And for this absolutely continuous evolution, now I can apply this game. Okay, and I do the same for the other, and then I'm done. Okay, so that lemma, that corollary, if you want, is what allows me to, to not care about how singular is the target measure in here. Okay, because in any case, it's going to be absolutely continuous, right? Or if you wish, actually, actually, I don't even need this limb of the entropy. This argument is already telling me that if the starting measure is, the reference measure concentrated to a set, then the constant C over there is really 1 over the measure of that set. And this already tells me, if you have a measure whose density is less or equal than, this is almost, when T is 0, this is almost 1. So if you have a measure that is less or equal than 1 over the mass of a set, in some sense, well, then the set where the density is positive should be at least the mass of the set. You see what I mean? And so end of the proof, basically, right? So we can repeat the same argument thanks to the fact that this estimate above does not depend on the regularity of the target. Okay. And now the rest follows, right? Because once I prove this, well, the rest is business as usual, right? Okay, that's a good point where to take a break, couple of minutes, and then with the with this happy perhaps let me just mention. Well, I don't mention. No, let us take a break, and then I start showing the proof of the split. All right. Sono sul Skype. Sul Skype, sì, 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 sì. Sì, 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 insomma. Ah, ah. All right. Let me sip the coffee and then we. Can you close, please? Thank you. Okay, what is the splitting theorem? Let me state first in the smooth category. This theorem by Chiger and Gomorrah. So let M be a Riemannian manifold. Smooth, complete, connected, no boundary. Okay, with non-negative ridge and containing a line. What is a line? A line is an isometry of R into the manifold. So a map gamma from R into the manifold with the distance between gamma t and gamma s being equal to s minus t for every t and s reals. So it's a curve that not only is a geodesic in some sense in the Riemannian setting of being locally minimizing, but it's really, globally minimizing. So something that, circles around, say, a cylinder would not be a line. Okay. Okay, then the manifold splits. That's what the splitting theorem. So that M is isomorphic to the product of some other manifold times R. In fact, I can tell you more. I can tell you, they can tell you that N is, of course, is a Riemannian manifold with a Ricci curvature of N non-negative. And the isomorphism here takes the form that X is being sent to, some, point P of X that I don't know what it is, but here, well, I should say, well, in fact, I actually let me put it. In fact, there exists actually, and there exists a map B, which is called the Busemann function that goes from M into R, with and such that the following two things are true. So if you compute B at gamma t, you exactly get T, and N, the manifold N is actually, the preimage of 0. B has, B is smooth with 0 Hessian. The Hessian of B is identically 0. The global Lipschitz constant, or also the local Lipschitz constant, is 1. And now I know who is this, the isomorphism is basically, well, here the isomorphism sends X. I want to go from here to here, and I'm taking X, and I'm sending it. Well, the second point is B of X, and the second point is, let me see, I don't know, let's call pr of X, projection of X, where this is obtained through a gradient flow. Well, pr of X, well, pr of X. I'll comment this in a second. Let me describe the proof of this, and then you see where this comes from. This sort of projection. I want to make a few comments on this statement. So first of all, from the purely geometric perspective, what here matters is this. If you have a so having on a Riemannian manifold, having a function with zero Hessian is already remarkable per se. Typically, you don't have this. And if you have, then locally the manifold splits. Okay. I will comment. I will be a bit more precise in a second. But here the point is that now you have a function which is a zero Hessian everywhere. So this local splitting becomes a global splitting. That's from the so here is where the splitting happens in some sense. Now, other comments. This is a rigidity statement. You should think of the splitting theorem as a rigidity statement. It's telling that morally, if you have equality in some inequality, then something special occurs. Let me explain why I'm saying this. There's an analog for the splitting for a positive lower Ricci bound, which is a theorem that I guess is by Obata. Well, perhaps there are two theorems that are there. So, theorem Bonnet-Myers inequality. So, if if the Ricci curvature of some manifold is greater or equal than k, and k is positive, then the diameter of the manifold is bounded from above by what? By the square root by pi square root of k divided by k times n minus 1. Something like this. And thank you. Yes, otherwise it doesn't work. Yes, thanks. Yes, thank you. Of course, thanks. Okay. So this is telling. A way of reading it is that if your manifold is more curved than the sphere, then the diameter is smaller than the one of the sphere. Okay. As here, Sn would have Ricci curvature exactly equal to n minus 1. So this is 1, and the diameter of Sn is exactly pi. Okay. Now, what happens if I have actually equality over it? As usual, when you have an inequality, you can wonder, well, is this inequality sharp? First of all, and if it is, okay, maybe if it is, I could actually find a manifold where equality occurs. Yes, the sphere. Okay. And but is the sphere the only case of equality? Would be interesting if this is the case, right? Because it forces you some structure out of an inequality, and this is the Obata theorem. Obata. Equality if M is the sphere, if M is Sn. Right? Okay. Now let's think of this case. So let's look at what happens when you let k go to 0 in this inequality. Well, first of all, for positive k, you cannot have a line because the manifold is bounded. As simple as it is. Of course, if you let k go to 0, the diameter blows up. So you are closer and closer to the possibility of having a line. Now, suppose that k is exactly 0, and you actually are in a case where you have a line. How does, of course, you would like to be in some sort in this situation, right? And the analog of the situation is splitting. So you are not a sphere, you're not Euclidean space. Huh? You are just a product. Okay. And it is clear that you cannot get more than this, because it is clear that if I start, from a manifold with non-negative Ricci, I multiply it by R, I obtain a cylinder which certainly contains a line. So it is clear that I cannot get more than this, no? All right. It has a long story, this theorem. So the first version has been proved by Convossen. It was in dimension 2. There was just one curvature, and basically said, look, if I have a surface with a negative curvature containing a line, then it is either the plane or the cylinder. And then it has been generalized first to lower sectional bound, and this is the version, the most famous one. By the way, so why is this relevant? Well, conceptually it is relevant because it gives you some structural result, right? And it tells you that the structure of a certain n-dimensional manifold is in fact totally dependent on the structure of n-1 dimensional manifold. Which is an improvement. Okay. And this is particularly even more. I mean, this sort of statement is particularly relevant if you study Ricci limit or RCD spaces, because of the following idea that goes by the works of Gigli and Golding that study rich limit spaces. So suppose you have a version of this for RCD. Okay, okay, you can wonder, even for manifold, you can wonder, well, it's fine as dandy, certainly it's a rigidity result, but how can you apply this? I mean, how often does it happen that you actually have a space or a Riemannian manifold with a theoretic containing a line? And in fact, Gigli and Golding, you notice that this happens often if you look at tangent spaces, right? So pick your arbitrary RCDKN space. K might be negative. Pick a geodesic on it, pick a point along this geodesic, not an extremal point, and blow up this space. So rescale this space by multiplying by some factor lambda, the distance very big, so that you converge maybe up to subsequences, use Gromov precompactors, you converge to limit space. Well, when you dilate the space, the lower bound, in some sense, tends to become a lower bound by 0. So your tangent space will be RCD 0n, okay? And given that this point was, along a geodesic, this in the limit became a line. Okay? So for free, if you know the splitting for either rich limit or for RCD, you know for free that tangent spaces at points, along geodesics must split a Euclidean factor. Okay, so that's already, you get an R out of this RCD sort of business. And now what is the Gigli and Golding said? Well, now start drawing all possible geodesics. And start looking, most of the points will be intermediate points of many geodesics. But if that's the case, those tangent spaces should split up a lot of R's. But it cannot be too many for doubling sort of condition, right? You have a doubling, the measure. And so basically, out of this, you can deduce, proper care, that for almost every x, the tangent space is Euclidean. Okay, and this is the starting point of any regularity theory. Yeah? So you start then saying, maybe you have charts, maybe of some regularity, etc., etc., etc. But in some sense, the starting of geometric measure theory is this sort of statement, for rich limits or for RCD spaces. Right? Okay. How do one prove this splitting theorem? Well, let me outline. Let me give you an outline of the proof. Without giving the details, I will give more details in this set of RCD spaces. But the starting point is the Laplacian comparison estimate. So it is a fact. Pick a point P in your manifold and pick as the function f of x 1/2 distance squared xp. Distance, of course, is the Riemannian distance. This. Then the Laplacian of f is less or equal than the dimension of f. Okay? What does it mean? Fact. I mean, this is Calabi. What does it mean, this? Of course, I can mean many things. So as a first approximation, this function out of the cut locus is smooth. Out of the cut locus, this inequality holds in the sense of, I compute the Laplacian and I get. But Calabi observed that, in fact, morally, this also, not morally, technically, this also works even at singularity points. Okay, Calabi worked in the sense of barriers. So basically, what he said was, look, for any x, I can find a C2 function touching the graph, touching f from above, such that and touching at x, such that at that point the Laplacian of the touching function is bounded from above at this. By the maximum principle, I can interpret this as a way of defining, Laplacian upper bounds. We in RCD we work with a different concept. We work with distributional Laplacian, but still, a good point of taking out is that even in the smooth setting, this inequality holds, even across singularities, and it is important that it works even across singularities, so that is a global sort of feature. Okay. By the way, another way of reading it is this is really Ricci curvature business. Of course, this comes from non-negative Ricci. Okay, and you can read this as follows: on RD, the Laplacian of x squared over 2 is exactly equal to d, the dimension of the space. Okay, if the manifold is Ricci greater than the 1 over d, then the Laplacian of the distance is less than the corresponding. Okay. So in particular, if we believe in chain rules, if we believe in chain rules, and we should, the Laplacian of the distance function from P, this is bounded from above, this should be equal to, distance function, Laplacian of the distance function, or it is, so this should be the Laplacian of distance squared over 2 divided by d, and then I should have what it is, Laplacian of this is d minus grad d squared, I guess. Still divided by d, still divided by, yes, right? I mean, I'm just saying that the Laplacian of f squared over 2 is f Laplacian f minus grad f squared. Okay, now, so this is less or equal. I have an upper bound on this, which is the dimension of the manifold. Okay, this is positive. Let me drop out. I mean, in fact, this is constantly equal to 1, but I can neglect. It's a negative term divided by the distance from P. Okay. So if I start, the Laplacian. So if I pick a very far point and I look here at what is the Laplacian of the distance, well, it is almost less or equal than 0. That's our ticket. Okay. Now here it comes a very important geometric construction, the construction of the so-called Boson function. This is a purely metric. Boson function. And this is the function B that I was speaking before. This is something that you can define as soon as you have a half line. So say that eta from 0 plus infinity to m is a half line, so satisfies the same identity that I wrote before, for every s and t, but this time non-negative, right? The half line. Well, then the Boson function basically gives a way morally of thinking about the distance from the point at infinity of eta. So I could define the function ft, actually bt, let me put it this way, btx. This is, so what I would like to work with is the distance between x and eta t. And I would like to send this to plus infinity. Of course, if I do, this blows up, so I have to renormalize. Let me subtract t, which, by the way, so if you want, this is, or if you want, let me subtract the distance between eta 0 and eta t. Okay, let's observe this in this function. So for any t, so this is defined for t greater or equal than 0. These functions are uniformly one-Lipschitz. And clearly, they are uniformly bounded, right? Because if so b of x, b of x, bt of x is bounded by what? It's bounded from above and from below, actually. The absolute value of b of x is bounded by the distance between x and eta 0. In fact, these are also, so I could already say that up to subsequences by Ascoli-Arzelà, they should locally uniformly converge to some limit. But in fact, I don't need any subsequence because there is monotone convergence. So BT, so there is an inequality. Now, I mean, is either BT less or equal than BS or BT bigger or equal than BS? Let's check which one of the two is true. So let's look at the picture. So this is eta, this is x, and BT is like this. So this is eta t, and BT is like this. I take this, and I subtract this. This is actually, this is beta t. Sorry, beta, BT. This is BT. And what is BS? Let's say that I pick, this is eta s. BS is this, minus this. Okay, now you see that there is a triangle inequality going on, right? So BS is smaller than BT, right? Because this yellow line by triangle inequality is less or equal than the green line plus this. But here you have equality because you are along edge of d6, so you get an right? Okay, so there exists a limit. So there exists b of x lim as t goes to plus infinity of btx. All right, and by that inequality, so this is purely metric. So this, I could state this in a metric space, and in fact, I do. I mean, not I, Boosman. Okay. This is purely metric. Now, if I couple this business with the Laplacian bounds that I have under negative Ricci, what I get is that I mean by passing to the limit in here, I get that the Laplacian of the Boseman function is less or equal than 0. I mean, I should work out how to pass to the limit on this sort of Laplacians, etc., etc., etc. But okay, and you see that in doing this, it is whatever it is important to be able to formulate this even on cut locus and as a global inequality, because when the point P goes to plus infinity, I have no idea whether I'm the cut locus if I have to exclude something or whatever. Okay, I need to pass to the limit of this. All right, but now we don't have an half line, we have a line. So we have a line, so we could define, we can define two Boseman functions, B plus and B minus, according to whether we are taking the lim as t goes to plus infinity of, the expression of bt, let me write, or as the limit as t goes to minus infinity of bt, in either case. Okay. Now, both these functions will be, what it is, subharmonic. Laplacian is superharmonic. Okay. Now let's have a look. Let's have a look to what happens. So I claim that B plus B minus at any point gamma t it is 0. And I guess this should be clear, right? Pick or if you want just a gamma 0. Okay. Who is B plus a gamma 0? Well, B plus a gamma 0 is the limit of bt in gamma 0. Bt gamma 0 is I take the distance from gamma t and then I subtract the distance from gamma 0. So this is 0. And the same for the vice versa. Right? So this is 0. Okay. And I also claim that there is a sign over, what it is B plus B minus over the whole manifold. And let's see what this sign is. So I claim that this is, always, on the manifold. And why is that the case? Well, let's look again at the picture. So I have, imagine, actually, let me draw the picture here. So I have gamma. This is gamma 0. Oh, sorry, gamma 0. How do I compute bt at some point? Bt at some point, I have gamma t in here, and I do this minus this. How do I compute b minus t? Let's say that this is gamma minus t. I do this minus this. But this guy is a geodesic. Now here I use the fact that gamma is really a line. So the distance between these two guys is really 2t. So if I add this up, I'm really adding, this distance plus this distance minus this distance. And so by triangle inequality, this is greater or equal than 0. Okay. But now here the strong maximum principle comes into play. Now here is an essential part for the rigidity. And the rigidity is, the Laplacian of the Boseman, both above and below, is greater or equal than 0. So the Laplacian of the sum is less or equal than 0. Okay. Now we have a function defined. Okay, I don't know how smooth it is. It's at least one Lipschitz. Okay, such that, but it's continuous in particular. The Laplacian is less or equal than 0. The Laplacian less or equal than 0 means morally that's like this. Okay. It is always non-negative, but it is 0 in some point. So this guy has a minimum on the manifold. By the strong maximum principle, this can only occur if this guy is constant. Does it make any sense? Okay. But if this guy is constant, this is the sum of two functions that were both of which were subharmonic. So this means that B plus must be equal to minus B minus. So B plus is harmonic. Yeah. Right? And now it's harmonic, so it's smooth. Okay. Okay. Now we have a Laplacian which is equal to 0, but I claim that you can arrive to Hessian equal to 0, which of course is a way stronger information. Okay. How do we pass from an information from about the Laplacian to an information about the Hessian? Well, in lower Ricci bound, there's only one way of doing this. It's always the same. It's Bochner inequality. Okay, let's have a look to Bochner inequality. The Bochner inequality tells actually, let me write down the Bochner identity. And the Bochner identity tells the following. It tells that for any f smooth, the Laplacian Bochner-Weizenbach identity, I should say. This is equal to the Hessian of f squared, the Hilbert-Schmidt norm, plus grad f, grad Laplacian f, plus the Ricci curvature in direction grad f, grad f. Okay. Now let's have a look at what happens with our Boseman function. So our Boseman function, so let's pick f equal b if you want. F equal b. Well, then we just proved that the Laplacian of b is 0. And okay, I did not prove, but I guess maybe you can believe me if I say that the gradient of b is identically 1. You think about the picture, huh? This is really important. It increases as I move, toward the direction of the point at infinity. Well, but then grad b squared is identically 0. So at the right-hand side, I have 0. And this should be equal to the Hessian of b squared plus, what about this term? Well, this term, there is a Laplacian of b. You do then whatever you want, but this is 0. Okay. So that disappears. Then I have plus Ricci, the direction of grad b, grad b. Okay. But of course, by assumption, the Ricci is not negative. So this forces the Hessian to be 0. Make sense? This is greater or equal than the Hessian of b squared, therefore the Hessian is 0. Okay. What do I do? So how I conclude from Hessian equals 0 to my splitting guy, my splitting principle? Well, now the point is this. So whenever you have, I state the thing globally, but you can see that if you want, I mean, it's easy to reformulate this in a local business. But now, let me define n to be the preimage, of 0. I claim that this is a smooth submanifold. And why this is the case? Well, if the Hessian is 0, the gradient cannot vanish, basically, right? So this is an affine function. So if the Hessian is 0, the gradient is constant. No? If you want the grad, no? There is the formula, no? grad b squared, if you want. So this is the Hessian of b grad b twice. So this, in our case, this is 0. So this is a constant function. So this is identically 1. So all points are regular points, or values are regular values, and the preimage is a smooth function. It's a smooth manifold. Okay. Now, this function b has 0 Hessian. Therefore, this manifold is totally geodesic. It's a convex subset. If you pick two points, in n, and you connect them by a geodesic, then the geodesic must lie entirely on n. And why is that the case? Well, pick gamma, geodesic in M, with b of gamma 0 equal b of gamma 1. I mean, that really works for any sublevel. Okay, and let's compute the second derivative of b along gamma t. So the first derivative is grad b in gamma t dot gamma t prime. The second derivative, given that this is a geodesic, if I throw the derivative on gamma, I get 0. I mean, we'll get the covariant derivative of gamma, that is 0. And then you have the Hessian of b and the point gamma t in gamma t prime, gamma t prime. But the Hessian is 0, so this is 0. Okay? But if this is 0, now I have a function, which is an affine function, because the second derivative is 0, and the value of the initial and the final point are the same. Okay? So this function is constant. Okay? So b is constant along geodesics, and therefore that's it. Well, but now this, the Ricci curvature of n being greater or equal than 0 is a is a consequence of standard formulas about manifolds and immersions and so on and so forth. So basically there's no curvature generated by how n is sitting inside M in some sense. So if you have a total isodynamic submanifold of a given manifold, whatever is the curvature bound on the manifold, this gets inherited by the submanifold. Okay. All right. And now what do I do? How do I define? So how do I move in some sense? So what's my splitting map? My splitting map is the following. My splitting map is the following. Now I can define the gradient flow of B. I can define, for every x. Well, let me define the map F. From M cross, if you want, R into M, define it the following way. So the curve that takes T and returns FTX is the only solution of eta T prime equal grad B at the point eta T, eta 0 equal X. So I follow the gradient flow of B. Now notice that if I pick F, apply it to X with time which is minus Bx, this will always live in my submanifold, sort of by definition. If I move along a gradient flow, actually perhaps the basic formula is that B at Ftx is B of X plus T. I guess B is 1 Lipschitz. I'm moving along a gradient flow, so B varies with speed 1 in some sense along its flow. Right? So if I pick a suitable T, I end up in the level 0. Okay, so let me call this map the projection map. So this really acts as a projection on N. And now my splitting map is the map that takes X and returns the projection at X, comma B of X. Okay. I've done everything. Let me just check now. I only have to check now. This is splitting map. That M is a product, but this is B. So yes, this is B as 0 Hessian. The Lipschitz constant is 1, and N is a level set, and there's no negative reach. Okay. What else? Perhaps what else is worth to point out? I wanted to say one thing. Okay, I don't remember. Okay, let me go on. So clearly, this is a map from M to the product of N cross R. Is it a bijection, perhaps? And yes, it is. And why it is so? Because what happens? So what happens? So if X and X prime have the same, projection, it means that they are leaving. So I have this manifold N, this submanifold, and then I'm moving along the gradient flow of B, the vertical direction. Now, if you know where a point is sitting in the projection, and B of X is, how far is the Boltzmann function, then you know the point. Make sense? And vice versa. So this map is injective, and it is surjective because, for any point in the submanifold, and for any real time, if I flow along the gradient flow for the correct amount of time, I reach, okay. And now let's check. So I want to check that M is a product. What does it mean that I have to check that M is a product? I have a map which is clearly smooth between Riemannian manifolds. So it is a bijection. So I really want to prove that the differential of this map is, is an isometry of tangent spaces. Okay, that's what I want to prove. I have a metric tensor on M. I have a product metric tensor in here, and I want to check. And by the way, what is the product? What is what it is the metric in here? Well, is the product metric in which the two factors are orthogonal at every point. the only one. Okay, here is the thing now. If I let me conclude in the following way. So if let me look at the level. Let me check that the differential of this map is an isometry on the level set on the points that are already on N, and then I comment how to deduce the same thing for other level sets. Now, if I have a point that is sitting over here, this tangent space clearly splits in two parts: one tangent space, which is the tangent space in N, and one vertical one. Now, on the direction of the tangent space in N, this map is an isometry. Pro is really X is really I move nothing, okay, and B of X is 0. So if I perturb X in the direction of the tangent space, the differential is an isometry. Make sense what I'm saying? Okay. And what if I perturb X in the vertical direction? So orthogonal direction of this. Well, if I perturb in the vertical direction, it means that I'm perturbing exactly the direction of the gradient of B, because this is a level set of B, so the vertical direction is really the gradient of B. But if I perturb in the gradient of B, I'm following the flow, the gradient of this guy. Right. These two components, the horizontal direction and the vertical direction, are orthogonal in M. And they are also orthogonal in the product. So that's enough to conclude. Okay. What happens at different level sets? Well, at different level sets, what you can argue in various ways. One way is to notice that the map that takes fixed t and pick the map that takes x and returns ftx. So I move along this gradient flow. This map is an isometry of M into itself, if you want, as a consequence of the fact that again the action of B is 0. Okay, so taking the level set 0 or any other level set is really the same. There's nothing special about 0. Okay, makes sense? I've been a little bit sloppy in this last part, but I will give more details in the metric setting, where in the metric setting, being a product should really be checked not at the level of tangent spaces, because that would be less clear what they are, but really at the level of Pythagoras theorem. Okay, we have triangles and they have the correct distance. Let me make one final comment, perhaps. Is the product? What is it I want to say? Perhaps, of course, in our more metric setting, we won't really have this. At least as of now, we won't have this book inequality written this way. We only have the one without the action. And still we need to extract information about the Hessian. So that will require a little bit of work, but a basic idea is this, and then I will stop. But the basic idea is that even if so let me just try to convince you about this. So suppose you only know that on your manifold, this manifold, so we are in a smooth setting, but we don't have, Buchner and Weizenberg never brought their identity. The only thing that they proved was that grad Laplacian of grad f squared over 2 is greater or equal than grad f grad Laplacian f for any smooth function f. Suppose you only know this. Okay, how can this be sufficient to extract information about the Hessian of B, for our Busemann function? Well, and the point is that our Busemann function will satisfy the equality here. Okay, while any other function satisfies an inequality. And this allows us to write an Euler equation for the Busemann function that basically encodes the same information that are encoded by this. Okay, so I guess this is in some sense just a preparation to what will come next. So on Friday there will be no lecture. Sorry, the lecture of Friday is cancelled. So the next lecture is next Monday. And what I will start doing next Monday is okay, I raise this Laplacian comparison on RCD setting. Okay, and then we start in some sense try to run this program in RCD setting and see if we reach that. All right.